Here we have 7.1 Matrices and Systems of Equations. A matrix is a rectangular array of numbers where we have a certain number of rows and a certain number of columns. And the setup is like this in these brackets. And this would be a 2 by 3 matrix because of the 2 rows and the 3 columns. So you write the first number as the rows, the second number as the columns. So if we look at the next matrix here, 1, 3, -8, and 0, there's 1 row and 4 columns. So this is a 1 by 4 matrix. An augmented matrix is a matrix written by using all the coefficients of a system of equations along with the constants that the system is set equal to. So here's an example of that. If we have 2x minus 2y equals, 2x minus 2y plus z equals 5, you would write that row as 2, -2, 1, and 5. For negative x plus 4z equals 11, you would write -1, 0, because there's no y, and so -1, 0, 4, and 11. And for the final row, we have 1x plus 3y minus z equals 0. So 1, 3, -1, 0. Sometimes books will put this line, this dotted line here, to separate the coefficients from the constants, and some books don't. But if you want to do that, it's a nice visual for yourself to know where the equal sign goes. And here I can know, okay, that final column is the equal values, and anything to the left of that line or left of that column are variable columns. So my first column here is my x, my second column is my y, my third column is the z. All right, there's a couple different types of formats of writing equations. And when solving a system of equations using matrices, it is similar to the elimination method and using back substitution when we were just working with equations. And the goal is to get the matrix into a form called row echelon form, or to reduced echelon form. Row echelon form is the one we will use because we can then just go ahead and do back substitution. All right, so row echelon form is when the leading entry of each row is a 1. So if we look at each row here, the first number that we have that's not a 0 is a 1. So you have 1, 1, 1, and actually all zeros, which is fine. And if you're going to have a row of all zeros, it needs to be at the bottom. It cannot be in the middle. The other thing about the ones, if you go from the top row all the way down to the bottom row, these ones are moving from left to right. Starting over here on the left, ending over here on the right. And because of each row starting with a 1 and these ones moving to the right, what happens is all these values down below are zeros. Okay? So that's row echelon form. Reduced row echelon form is all of that and the zeros above the ones are, the numbers above the ones are zeros also. So here you have the ones, you have them moving to the right, you have your zeros down below, and you have zeros above the ones. Okay? And here's an example of something that's not in row echelon form. The ones, you can see they're scattered going from left to right and zigzagging back and forth. and obviously this is not row echelon form. Okay? You cannot have reduced row echelon form without having row echelon form. Okay? All right, let's see what's next here. We're going to take this system of equations and we're going to write it into an augmented matrix, and then we are going to solve using Gaussian elimination method. And this is using elimination method with the matrix. We're going to get this to the row echelon form and then use back substitution. So when we look at this, I'm going to write this out, and I have 4, 8, -4, and 4. 3, 8, 5, -11, -2, 1, 12, -17. Okay, and I can put that dotted line there, dashed line, and that kind of separates and shows me where the equal sign is. Okay, so if you remember row echelon form, our leading entry had to be a 1. So we're going to start in the top left here and kind of work our way down to get to our diagonal ones. Okay, remember we want the diagonal ones, we actually want them to be 1, 1, and 1, straight diagonal. And then this corner here, this bottom corner here is going to be zeros. Okay, so we want 1, 0, 0, whatever these numbers are, 1 and 0, whatever numbers are here, 1, and then whatever number is there. And that's what we want to achieve, because by doing that, we will be able to say that z is equal to whatever number is there. And then we take that, plug back up into the second row to find y, and then plug back up into the first row with your x, your y and z to find your x. Okay, so that's what we're trying to get to. So the very first thing I have to do here is divide this first row by 4 so that I can get a 1. So we're going to divide this by 4. If I divide by 4, I get 1, 2, -2, 1. Okay, and then my other rows stay the same. Okay, the second step is to get this to be a 0. When I'm getting the zeros here in the first column, I'm going to use the first row because that's where my 1 is that I just got. So to do that, I'm going to take the opposite of the number I'm trying to get to be a 0. So I'm trying to get this 3 to be a 0, so I need -3. And I'm going to multiply row 1 times -3. It's supposed to be a multiplication. Okay, so step 1 was to get a 1 at the top left corner. Step 2 is to zero out the second row, the first number. And if I multiply row 1 by -3, I get -3, -6, +6, -3. I write down my second row here. I'm going to add these together. I get 0, 2, 11, -14. Okay? So I'm going to write my second row as this new set of numbers here that I got when I added -3 times row 1 plus my row 2. Okay, so that's what my operation was. The next thing I want to do is get a 0 down here at that -2. So the opposite of -2 is +2. So I'm going to take +2 times row 1 to add to row 3. and that will give me 0 down on that bottom left. So 2 times row 1 is 2, 4, -4, and 2. My third row is -2, 1, 12, and -17. When I add these together, I get 0, 5, 8, -15. Okay, I realized I made a mistake here. Hopefully you caught that before and saw that I was doing that incorrectly. But anyway, I'll go through and fix that. So when I divide the first row by 4, that's 1 to -1, 1, because -4 divided by 4 is just -1, not -2, which makes this, when we multiply that times -3, that will be 3, which then makes 3 plus 5 to be 8, which makes this over here 8, and yep, right here would be multiplying row 1 by 2. Would that make that -2? And this would be 10. Wait, yes. Okay. So then, okay, we've added 2 times row 1 plus row 3. We get 0, 5, 10, and -15. So 0, 5, -10, and 15. Okay, and this is what we achieve, is this new matrix. And as you can see, I have my 1 up here on the top left. Underneath it, I have my zeros. So now I need a 1 right there. So I'm going to divide by 2. Now, it doesn't matter if I get fractions over here or not. I just have to get that to be a 1. So I have to divide by whatever that is so that I can get a 1. So that will then give me 1, 2, -2. Nope, I didn't change this one over here. 1, 2, -1, 1, 0, 1, 4, -7, 0, 5, -10, and 15. All right, so I've got my 1, 0, 0. My leading term here, my leading number is a 1. Now I need to get this 5 to be a 0. So now that I'm getting the second number to be a 0, I want to go to the row that has the second number as a 1, which is row 2. I don't need row 1 anymore, so because I have those values as zeros. So I'm moving on from row 1 to row 2. So to zero out the 5, I need -5, and I will multiply row 2 times that -5 to add to row 3. So that's going to give me 0, -5, -20, and 35. My row 3 is 0, 5, -10, and 15. When I add these together, I'm going to get 0, 0, um, oh, this should be, let me check this here for a second. All right, so I am having some difficulty here. This was 0, 5, positive 10, negative 15. So I had the negative in the wrong spot for over here, which then put the negative in the wrong spot over here. So when I add now, I get negative 10. When I add here, I get 20. All right. So that's going to replace row 3. And I'm going to have 1, 2, negative 1, 1, 0, 1, 4, negative 7, 0, 5, 10, and negative 15. And when you look at this, I got to replace the row 3. Okay. I have my new row 3 as 0, 0, negative 10, and 20. Okay. I have my 1, 0, 0 in the first column. When I go over, I have my diagonal 1 here with a 0 below that. But then I need this third diagonal value to be a 1. So right now it's negative 10, so I need to divide by negative 10. And when I do that, my final matrix will be right here, 0, 0, 1, and negative 2. Okay, so, and if I draw that dashed line there, okay, if I kept doing that throughout, you can see I've got my little square to the left here is a diagonal of 1s. And my zeros down here in the corner. So now I can tell you that z equals negative 2. When I go up to the second row here, the equation written from that is 1y plus 4z equals negative 7. So if I plug in negative 2 for z, I can solve for y. So that's negative 8. So I'm going to add 8 to both sides, and I get y equals 1. And then I'm going to take and plug y and z into the first equation. My first equation is x plus 2y minus z equals 1. So x plus 2 times 1 minus negative 2 equals 1. So that's x plus 2 equals 1. 2 plus 2 is 4, so I'm going to subtract 4 from both sides, and I get x equals negative 3. Okay, so I've got my x, y, and z, and now I'm going to write this into an ordered triple. All right, so that's how you solve for a system of equations using matrices and using Gaussian elimination method. Okay, now a couple things about different types of solutions. As you had with regular systems of equations, you could have um, solutions that are none or no solutions. for infinitely many solutions. Whenever you end up having no solutions, this is an inconsistent system. Whenever you have infinitely many solutions, this is a dependent system. Okay? Um, so let's look at an example where you would end up with no solutions. Okay? If you work through all of this work that we did right here, just for this example, but you end up the final matrix after working through the Gaussian elimination method is going to look like this. Okay, you're going to have, whatever, 1, -3, 2, 12. Now, these are just random numbers. Okay, it's not exactly what you're going to end up with every time, but you're going to end up with having something look similar to this, where you're looking at a row that ends up with all the variable numbers, coefficients, are zeros. Your constant is a number, a non-zero, and this is trying to say that you have no variables, but you still have an answer of 18 in this case. Okay. If you ever end up, after working through all the work, if you ever end up having zeros and then a number, that is a no solution. So right here in this row would tell us, oh, we have no solution. Okay? For infinitely many solutions, infinitely many, okay? You're going to work through all the same work, okay? The final matrix will look like something like this. Okay, 1, 0, -7, -5, 0, 1, -3, 1, 0, 0, 0, 0. Okay, so do you see the difference between no solutions and infinitely many? You have all 4 zeros, not a number at the end like 18 up here, but a 0. And yes, the 0 is a number, but a non-zero. Okay, up here you have a non-zero. Up down here for infinitely many, it's all zeros. So infinitely IMS, infinitely many solutions. And at this point, you're going to write an ordered pair in terms of a variable. Our book likes to use t. So here we're going to say, let's say that z equals t. If we go back up into the second row where we have y minus 3z equals 1, we plug in t, so y minus 3t equals 1. Solve for y. I'm going to add 3t to both sides, and I get y equals 1 plus 3t. Okay, so I'm coming up with variable expressions for x, y, and z. So now that I have z and y, I'm going to go up to the first equation where I have x, no y, so minus z, 7z, equals -5. I'll go ahead and replace z with the t. I get x minus 7t equals -5. Add 7t to both sides, and I get x equals -5 plus 7t. And so now I can write it an ordered triple, even though I have infinitely many solutions. So -5 plus 7t is my x, 1 plus 3t is my y, t is the z. And that's my way of showing a more focused um, solution for my infinitely many solutions. Infinitely many, you just have every possible number out there to consider. When you have this ordered triple written out with these expressions, if I know a value for t or x or y, I could quickly solve and find out what that ordered triple is going to be. Okay, so that would be the purpose of writing that ordered triple. And that's it for 7.1.